All right, well, I'll get going here. As mentioned, I'm Steve Spatz with Efficiency Vermont. I work with our EEN contractor in networks and all the various trades that we represent in the EEN, and work as an energy consultant as well in our residential programs. So I'm going to talk to you this morning about air-to-water heat pumps, an overview of the equipment, opportunities with the equipment, and what differentiates air-to-water from other heat pump options, and how air-to-water equipment can be integrated into both existing buildings and used in new construction applications. We do have AIA credits available for this session here today. So if you are an AIA member looking for credits, there will be a link in the chat that you'll be able to go and link into to submit the information to AIA for. We'll also get credit for you, any of you who are EEN members who are joining us today. You'll get an hour CE credit for the year for attending today's session. And if you don't mind, at the end, there'll be a brief survey at the end of the presentation here today. Just some feedback from us is always helpful to know that we're on the right track, or looking for new opportunities, new things to discuss, new ways to go about it. So appreciate your participation. If you got questions as we go along, feel free to raise your hand, or speak up, or drop it in the chat. I'll make sure to stop as I move along here and make some time for questions. But feel free to participate. I appreciate the participation as we go along. All right, so air-to-water equipment. Go through, what heat pump equipment can do, what the options are. Heat pumps are a heat transfer mechanism. So we're talking about moving heat energy from one place to another via the refrigerant cycle, and using the differences in pressure and temperature and phase change in the refrigerant itself as a way and the mechanism for moving heat energy. Heat pumps have served a variety of purposes for a very long time at this point, and space conditioning, they've been a part of the equation for decades as well. The most predominant application we've seen here in Vermont in the Northeast in the past 10 years, 15 years is air-to-air heat pumps. So, the mechanism there is you're simply just moving air across the hot refrigerant coil to blow warm air or cool air when that refrigerant cycle is reversed into a room for space heating. Water or ground to air is more like a geothermal type system, where you're taking heat energy from the ground at a consistent temperature, typically over time, over heating season, cooling season, and you're either extracting heat energy from that ground or water source, or rejecting heat energy into that source on the cooling side of the equation. And both ground or water source heat pumps can be used to transfer that heat energy into an air distribution system or a water distribution system. And then finally here, we're talking about air to water. So we're using the same sort of outdoor condenser evaporator unit that you'd use for an air-to-air heat pump, but the mechanism for the distribution side of the equation for moving the heat energy within the building is water. So where we're talking about air-to-water heat pumps is more in a whole house application than we are in the use for air-to-air heat pumps or mini splits. Most typically you can consider those as space heaters. They're not a distributed system, so you're heating the space that the heat pump unit is located in and associated with. So when we're talking about air-to-water systems, we're talking about getting into whole house heat pump systems. So looking at both ducted and hydronically distributed systems. So, as I mentioned, air-to-air heat pumps have been the most predominantly installed so far in the state, because they're a relatively easy installation, and there is a lot of applications for them for picking up loads in existing homes, providing space conditioning for both heating and cooling where there wasn't before in a building. And as we've been getting better and better building envelopes when it comes to new construction, and the ability to be able to retrofit existing buildings quite well too, the opportunity of looking to heat and cool those buildings with heat pump equipment has been a part of the new construction equation as well too. So you do still see air-to-air wall-hung heat pumps used as a way to create space conditioning throughout a whole building. But there are some limitations in the ability to do that. You are moving air across a refrigerant coil, so you're blowing air into a room, and if you're doing a retrofit application and the occupants are not used to having air moving in their space, that can be something for them to adjust to. It can be challenging. There are controls on the market now that can better integrate using ductless systems with existing heating systems in the building to kind of control one is running versus the other. But there are definitely, it's not an integrated system out of the box. Space for the equipment, placement in the room, those are all considerations about using ductless heat pumps. And when you start to try to condition an entire building, you end up looking at multiple heads that are required throughout the building. To get the most efficiency from most air-to-air heat pumps, a single one-to-one arrangement is typically provides the best performance. So you can end up with a lot of equipment in a building to create a fully distributed, for what it can be, heat pump system. So considering that, we're looking at what the difference is between the medium that is being used to transfer heat energy in the building here. So what we're looking at here are some examples of how to illustrate basically the same concept in 3 different ways. So we're looking at expressing what the carrying capacity in BTUs for various materials and different mechanisms of moving heat or cooling energy in a building. And what we're comparing here is for, typical building, you're looking at either an air distribution system or a hydronic water system for distributing heat energy in the building. Water has a much higher carrying capacity of BTU per volume than air does. And, looking at the chart here, you can see just the BTUs per square foot of capacity. Water will carry 62.4 BTUs per cubic foot versus less than a tenth of a BTU for that same volume of air. And to illustrate this in an example, as you'd see an application in a building, this 14 by 8 inch duct right here carries the same amount of heat energy as this 3/4 inch piece of copper tubing. So when you start to consider the distribution side of the equation and moving, what you need for distribution throughout a building, there's typically much less physical infrastructure required to do a hydronic system than you would need to do an air system. In conjunction with that as well too, you're looking at what the other embodied energy is that's required to move that heat energy from either the boiler or the furnace. So you're talking about additional energy required to actually move that medium, whether it be air or water. And if you look at what it takes as far as relative comparison of consumption energy, electrical energy to move that medium, you're putting out a lot more energy to move an equivalent volume of air than you are to move that same amount of liquid, of fluid, of water. So there are definitely efficiency gains by looking at hydronic distribution. Hydronic distribution can serve various applications within a building at coming from the same manifold essentially, which we'll touch on here in a little bit when we go into the distribution options as far as what you can use in the building for distribution. You have, a wide variety of options for placement of where you want to put the distribution for hydronic systems. Again, if you're doing a ducted air-to-air system, you have to accommodate for the significant size of the ductwork throughout the building and make sure that there is structural accommodation to move those ducts as well. Moving air within the building, what if it's done well can be quiet, but at times if you're not doing, they don't have the flexibility with the duct system, it can be a noisy system as well. So we do have a lot of hydronic systems in the Northeast, and actually it's probably the most highest volume of, or highest amount of hydronic systems in the US is in the Northeast. So we have a lot of experience in the contractor base of doing hydronic systems and using water. And it also opens the door for, you know, retrofit, but we're going to talk about some of the retrofit considerations when we're talking about using air to water equipment. So that being the case, the traditional baseboard hot water heating system carries relatively hot water. You know, you're using a fuel-fired boiler that is creating a large volume of BTUs in the combustion of that fuel, and creating much hotter water than that is used to distribute throughout the building. And the, you know, determination of the amount of surface area that's needed for baseboard or radiators or whatever other distribution equipment you're using in the building is related to the temperature of the water that you're putting through it. So if you're putting high temperature water through a baseboard, you know, you get a pretty high volume of BTUs out of that tubing or that baseboard, you know, relative to the length of what's in the room. When we're talking about using heat pump equipment, and this goes for both air to water and for ground source, heat pumps they move heat energy and they move it efficiently, but the volume of, or the amount of BTUs available to move is somewhat confined or restrained compared to just the high volume of BTUs you create when burning fossil fuel. So any heat pump system is going to be creating lower temperature air or water by way of that refrigerant heat transfer mechanism. So when we're talking about air to water systems and geothermal, you know, we're getting away from a temperature range here of 145, 150 up to 180 or 190 degrees, which is a typical distribution temperature for baseboard or radiators and other hydro air distribution. We're now talking about using water that's between typically 100 and 120 degrees. Most air to water heat pump equipment is kind of designed around the optimization of using 120 degree water as your distribution temperature. So your emitters and what you're going to be using to transfer that heat energy in the building is going to be designed around moving 120 degree or lower temperature water. So we need more surface area for that to matter, or for that to work. So, you know, thin slab radiant floors, low temperature baseboard where you're getting more surface area for the water that's moving through it to be, exposed to the room. These are typical applications or typical distribution types if you have control over putting in a new distribution system or retrofitting an existing distribution system. So that's a consideration when you're talking about the use here, whether it's for new construction or for retrofit. In a new construction situation, you have, you know, as much flexibility really as you want to define what your distribution type is going to be and optimize that distribution around getting to the lowest temperature water that you can. And whereas in a retrofit situation, you need to consider how you're going to create the same amount of BTU energy in the building with less surface area based on the type of distribution that's already in place. That means you either have to retrofit what's in place for distribution or add more distribution of the same type of what's already there. So there are some considerations and challenges when it comes to retrofit. But if we're talking about the future of where we're looking at for flexibility with heat source equipment, you know, heat pumps are here to stay, and they're a highly efficient mechanism for transferring heat energy for doing both heating and cooling. And you have the flexibility to do both heating and cooling with hydronic systems. And any system that is designed for moving water, a hydronic system, and is designed around low temperature water is going to be the most flexible and the most efficient, no matter what fuel type you're using. You know, low temperature distribution will make a gas-fired, you know, propane boiler, a condensing boiler, condense and be, you know, serve its most potential efficiency as well. So, you know, low temperature distribution is really a focus of what you need to be considering when using geothermal or air to water systems, and again, getting the most out of fossil fuel systems as well too. Having flexibility, with hydronics, like I said, you can really put that heat energy where you need it. You have a lot of control over zones and localized control throughout the building with hydronics, because you're just shutting down and restricting flows or opening flows to various places within the building. You have more consistent temperatures and less stratification of air in the building with using hydronics. So these are all considerations. You can do hydro air with air to water, meaning that you can put a hydronic coil into a duct system and air handler and move heat energy throughout the building with a ducted system with air to water equipment as well too. But again, that has to be optimized around the lower temperature water that is going to be created with the heat pump versus what you'd get with an oil or propane or natural gas fired boiler. Take a quick stop for any questions there around kind of just the basics of the equipment, how we're transferring heat energy here. Any questions? All right. Oh, I'll keep rolling. So some pros and cons. As I mentioned, there's a lot of hydronic equipment in place in the Northeast. So we do have a skilled contractor base that is used to working with these systems. An air to water heat pump is really just a device for creating the heat energy you need to transfer and move throughout the building. So the only real, fundamental system difference here is, again, designing for low temperature water distribution, and then the piping and the connection of the heat pump to the distribution side of the building. Otherwise, these are not magic boxes. There's nothing fanciful about them. There's no, major, complications to how the equipment operates or how it needs to be set up. You're simply just creating an optimized distribution system that fits well within the temperature capacity of the heat pump itself. And just to kind of illustrate the point I've been making here is that, the kind of go-to for many years has been to use a modulating condensing gas boiler as your way to have flexibility in the different ranges of BTU needs a building will have throughout the heating season. So, when you're doing your load calculations for a heating system, you're basing your BOC load, your building load, on what a worst case scenario sort of condition would be. I mean, in Vermont, the design temperature is usually -11, somewhere between -5 and -11 as your design conditions. So that's going to be, the basis of design for what the most BTUs will be needed on that type of day during the heating season. But the bulk of the heating season is going to be above that temperature, meaning that your capacity or your heat requirement for that building, your BTU requirement for that building, is going to be lower than what the maximum capacity of a sized boiler could potentially be. And what you don't want to get into the situation of is having either gas-fired boiler or a heat pump or whatever you're using to be putting out too many BTUs or too much heat energy for the bulk of what the heating season requires. And you can, when a condensing gas boiler is not operating at a good temperature range where it's putting out the BTUs into the distribution side of the equation, moving heat energy into the building, all that heat energy needs to be rejected in the distribution system before it comes back into the boiler on the cold side return. And if it's not able to put out all of those BTUs into the building because you're putting out too much heat to begin with, you're getting warm water back into the boiler and it doesn't condense. And so you're not getting that high efficiency performance out of the equipment under those conditions. So that temperature range, when you start to see the condensing occur with a propane boiler, aligns with, the temperatures of where we're talking about with what a air to water heat pump would be generating for distribution. So, you know, we're still, this is your target range, you know, between 100 and 140 degrees of what you should be defining for getting your temperatures out into the building is going to be the optimal fit for an air to water or geothermal heat pump system, and also be the most efficient for using a gas type boiler as well too. This is just an illustration about how the efficiencies come into play here. You know, when your options, depending on your distribution system of what you're setting your distribution temperature to. This is the COP, or performance, you know, efficiency of the heat pump, and outdoor temperature here. So you can see if you set the distribution system at 130 degrees, when it's 8 below, you're going to have a coefficient of performance, you know, about 2.25 in this example here. Whereas if you start to be able to lower your distribution temperature in the building, which is dependent on the building envelope, you know, and your loads of what the building actually requires for heat, and how well you've distributed your surface area for heating throughout the building, you can start to lower that distribution temperature. And the lower you go with that distribution temperature, the better the efficiency of the equipment becomes. So again, optimizing around low temperatures here. The distribution system really should be thought of as a permanent system. You know, if you get that dialed in and done right, designed around low temperature, you can plug whatever equipment you want into that now, or 10 years down the road, it's still going to work, you know, efficiently, unless something magical happens on the horizon that changes fundamentally how we heat and cool buildings. So it's a big part of the equation here. Again, you know, the heat pump itself, the air to water heat pump, is not a magical box that does anything more unique than another type of heat pump does, but how it works within the building is really the, you know, the piece of the puzzle to get right. So any questions? Chat here too. Okay. So what are we talking about for distribution options here? So again, we're talking low temperature, so low temperature emitters. One of the most popular or common ways of doing this is with radiant floors. So there's a variety of ways you can do radiant floors in modern buildings. You know, low mass systems are really what make the most sense for lower temperature water distribution, not high mass systems. And when I say high mass, I mean, you know, radiant tubing in a 4-inch thick concrete slab. That's considered a high mass system. That's a slab that is going to gain heat energy slowly and then lose heat energy slowly. And there's, you know, you can experience significant swings to some extent when you're trying to when you have a low load building and you're trying to really just modulate the temperature within the building. And that's what matches well with a heat pump. You know, a heat pump is designed to not come on and off and cycle on and off. The efficiency from a heat pump comes when it's modulating along and adjusting and ramping up and down to meet the demand within the building. And similarly, low temperature emitters, you know, have that same, it's that same concept. You're slowly and moderately adjusting the BTUs move through those emitters to keep the rooms comfortable. So radiant systems for framed floors, for you know, typical framed assemblies that are not concrete. You have under subfloor tubing, where you're stapling up tubing to the underside of the subfloor and then using aluminum pans basically to help create more surface area to move the heat from the tubing to expand across the subfloor. You have above subfloor radiant track systems, where similar concept to this, but you're putting your tubing on top of the floor and then your finished floor goes directly over top of this. And there's various versions of this product out in the market. And then this image in the middle here is a gypcrete, or a thin masonry pour over the tubing on top of the subfloor too. So the same concept applies with all of these, is that you're trying to, you know, you're moving warm fluid through this tubing and then trying to use aluminum or this gypcrete, other ways to, you know, expand that heat energy into the surface areas around the tubing. This same concept can be applied beyond the floor as well too. You don't see this done as often, but certainly there are examples of this being done in the Northeast, and we've seen this done before. And this is actually, you're doing the same concept. You're using low temperature PEX tubing and using aluminum panels to create the surface area, and is applying this in a wall or a ceiling rather than in a floor. You can do cooling with these. You have to be careful within your design range of what water it is you're putting through that, and manage indoor conditions as well. But this does provide some flexibility within the building. If you're doing a radiant floor throughout the majority of the building, but you have some design considerations that keep the floor from being a viable option in one part of the building, you can move this same concept to walls or ceilings. Panel radiators, same sort of concept as old cast iron radiators essentially, but you're creating a large amount of surface area and then moving that warm water through a coil in here with aluminum fins, and just creating large amounts of surface area to heat the space. These panel radiators typically have zonal controls on them, so you can adjust the temperature and the flow into the room at the unit itself. There are panel radiators that have fan coil assisted as well too, so it's kind of like a squished down and condensed version of a wall hung mini split, where you've got your refrigerant tubing here and your aluminum fins, which is where you're getting your heat transfer. But then you have low voltage fans that are moving air across those refrigerant coils and moving that air into the room. And some of these, as I said, with the controls that you have on them, you can control, what the BTU capacity is of that panel radiator in each room. Low temperature baseboard is, same concept as standard fin tube baseboard, but again, you have to create more surface area. So, you're talking more copper tubing and then tighter aluminum fins and just larger surface area to begin with. And, these and the panel radiators here are viable retrofit options for existing buildings. So if you have a situation where you're looking to replace a boiler in an existing home with an air to water heat pump, or augment the use of that fossil fuel boiler while retaining it, and you need to create more surface area to get the same BTU capacity in the rooms that you're trying to condition, these are some of the sorts of things that you can retrofit into an existing building without needing to tear, a large part of the infrastructure up to do so. And then hydronics, like I said, offers a lot of flexibility, and manufacturers of air to water equipment out in the market do have wall hung fan coils. So same concept as a air to air mini split, where you can use these in rooms and you're running that coil or that hydronic coil through this, and you can do both heating and cooling with these sorts of wall and floor mounted units as well. And as I said before too, you can do a hydro coil where you're running a hydronic coil into a air handler and doing an air distribution system in the building. And with the flexibility of how you manifold off of a boiler or an air to water heat pump or a geothermal system, there is flexibility to be able to do multiple different distribution types in the same building. So conceivably, you can have a radiant floor on the first level, panel radiators on the second floor, and then a ducted distribution system for air on the third floor of a building, all being fed from the same distribution system. So, the same air to water heat pump, which is creating hot water in a buffer tank, and then that buffer tank is being used essentially as a thermal battery to feed these different distribution types throughout the building. So just one more visualization of reiterating the same point, of the progression of where we're going with how we heat and cool our buildings and the intensity of what we've needed to do in the past to keep our buildings comfortable. So as our buildings become more efficient, better insulated, more airtight, lower load buildings to begin with, we do not need the same amount of heat energy to keep those buildings comfortable. And the lower we can go with the distribution side of the equation, the more flexibility we'll have with time for options. I'll pause again here for any questions. Okay, we'll talk about some products. So quite a few different manufacturers in the air to water world here. And this is equipment that's been used around the globe for a long time. Similar to, when air-to-air systems and mini splits became viable here in the Northeast and in cold climates, it wasn't a new piece of equipment that we were seeing brought into our state and the region. It was basically just a optimization of existing equipment to work with cold outdoor ambient temperatures. And this is similar to where we're at with air to water equipment. The same mechanisms are in place as an air to air when you're talking about what the outdoor unit does. So using the same types of refrigerants and the same sort of variable speed compressors, we're getting more equipment on the market that works for cold climates. So the predominant manufacturers and equipment that we're seeing used and installed in Vermont and the Northeast, Aramec, Arctic, Chiltrix, Nordic, Spacepak, Enertech, Taco. Some of these are products that are available as far as access to them in our market. We're predominantly seeing Spacepak, Nordic, Chiltrix, Arctic, and Aramec. Spacepak is available through FW Webs. Aramec is now being carried through FW Webs. Nordic, Chiltrix, and Arctic are kind of direct consumer sort of sales, so you work with the manufacturer directly. And there's different configurations here too, Monobloc versus split systems, and I'll mention that in a moment in more detail. But the basics is that a Monobloc system is actually moving a glycol loop of water to the outdoor unit, whereas split systems are simply a refrigerant transfer mechanism, and the heat exchange from the refrigerant to the water side, the hydronic side, happens inside the building. Looks like there may have been a question. Kim's note here, a large retrofit system could be very expensive, which makes air to water heat pump incentives tiny in comparison. Any plans to increase them? Asking a homeowner to replace all their baseboard usually means they won't even consider this. Yeah, no, that's true. And that's where we're at with this equipment, is that it's from the consumer side of things, it seems to be like a no-brainer. You can just, drop this in to replace your existing boiler and have a fossil-free fuel system in your home. But as I mentioned, and as you note here, Kim, yeah, it takes more consideration than that. So it takes an evaluation of what the actual conditions are. Definitely there's retrofit applications that work. And really this ultimately comes down to knowing what your loads are for the building. You need to know your block load for the whole building, but you also need to know what your room by room loads are, and then evaluate what is already existing in those rooms, and if there's capacity there to serve the room with lower temperature water than what's already going through it. The air to water systems can be integrated into an existing oil or gas fired boiler system as well too. You don't need to always just remove that existing boiler. You can use the air to water system to do the majority of the heating, and then if you don't quite have that BTU capacity as you need it room by room on the coldest of days, that fossil fuel system is still there to back that up and keep those rooms conditioned. So yeah, the incentive side of things, I mean, right now the incentive on the equipment is $1,000 a ton, actually, which segues well into the next slide. So $1,000 per ton of capacity, and a lot of the equipment that's available on the market is usually in the 3 to 5 ton range. So, you know, prices vary on this stuff, and depending on what components you're buying from the manufacturer directly as well too. But you know, the intent with the incentives on this is to try to bring the cost of the air-to-water equipment closer to the cost of what it would take to install a high efficiency gas boiler or something equivalent on the fossil fuel side of things. It's not a equal one-to-one comparison, obviously, but you know, the bulk of the install cost here really still is on the distribution side of the equation. You know, you're going to do the distribution to whatever temperature you want to get into the building for what it's going to be, and then is a matter of choice as to what equipment you're going to use to create that heat energy for the building. So monobloc versus split systems. Monobloc systems, which is what kind of the air-to-water equipment started out as being kind of just universally, was these monobloc systems where the heat exchange from the refrigerant to the water was actually occurring outside. So you were piping water with glycol loop to the outdoor unit. The heat exchange was occurring there and then piped back into the building. There's a lot of equipment out there that is monobloc and has been installed and, you know, in use in Vermont for many years at this point. So it does work in cold outdoor ambient temperatures. You get your glycol loop, you know, percentage correct and insulate the line sets well. There hasn't been any issues that I've been, you know, aware of freeze ups or anything like that have occurred. So there are, you know, some considerations in using monobloc versus a split system. The split system is that, as I mentioned, that heat exchange is happening inside the building, which the next slide will show. But you don't need to be doing any refrigerant connections in the field because that's all inside the box, outside, the outside unit. And, you know, you don't have any operational equipment of that heat pump mechanism that's within the building. Everything is outside of the building, so you don't have the noise of the compressors coming on and running within inside the building. The split system, though, is more, you know, is basically the same sort of arrangement that you'd have with an air-to-air heat pump situation, where you have an outdoor unit and an indoor unit. You have refrigerant piping connecting the two, and then your heat exchange to your distribution side of the equation happens within that indoor unit. So going back to manufacturers, Spacepak had their LAHP monobloc system on the market for many, many years. They've recently changed their product line. They now have a split system, split inverter system, and then they also have an updated monobloc unit as well. Chiltrix and AirMech are also monobloc systems. This is an old picture. Dakin has air-to-water equipment, but it's not sold here in Vermont, or even, I don't even know if it's sold in the US anymore, but it was available years ago for a brief period of time. But again, this was not optimized for cold climates at that point, and so they pulled out of the market. Nordic is another popular air-to-water manufacturer that we've seen installed quite a bit here in Vermont, and is a split system as well. So pros: no need for glycol. You know, the system's more protected by being inside. You do need someone with a refrigerant license to set this up, and therefore also, you know, you need to make sure that you're charging the refrigerant properly. You know, because just like with any sort of refrigerant system, if it's poorly charged and it's not leak tight, then you will have issues with operations. And you do need to make sure that there's space for that indoor unit to be placed as well. And we're not talking large size infrastructure here as far as what the equipment will be in a building to take up space. So we're looking at COPs for this equipment, just like you would with other heat pump equipment when you're looking at its efficiency over the whole, heating system of taking into account the energy involved with running the fans, moving the system, moving refrigerant and everything else. So, COPs are not going to be listed on RE. So you're looking to get the performance data from, for air to water equipment, it's pretty much coming from the manufacturers. The NEEP registry of cold climate heat pumps only has a criteria and listings for ducted and non-ducted equipment. So air to water equipment does not have a criteria on NEEP listing, so you won't find air to water systems listed through NEEP. So we're pretty much going off of manufacturer data here. And the COPs, as I was kind of showing some of these other charts here, really is dependent on your supply side temperature and what you're actually creating, what it is you're creating for distribution temperatures through the building. So the lower you're going with those distribution temperatures, the better that your COP is going to be for any given equipment. So a couple examples of just some basic layout design here. You have your outdoor unit. This is a split system. So you have your outdoor coils piped into the indoor unit where the heat exchange occurs. We're using buffer tanks for these systems. That buffer tank is going to be sized based on what it is you're planning to do with the heat pump for the building. So you do have the potential and the capacity to do not just your space conditioning with this, but also domestic hot water use. You can set this up to be able to do heating, cooling, and domestic hot water. So sometimes you're going to be having multiple tanks rather than just one. But that buffer tank serves the purpose of creating the thermal storage to then be used for your distribution of whatever type throughout the building. Having that tank be stratified is part of the design consideration here too, where you're trying to not have a lot of mixing occur within the tank to get that better, modulation of temperature through the distribution side. And again, from here, you have a lot of flexibility about what you can do from the buffer tank. This is your primary connection here of the equipment to thermal storage, and then from there, you're feeding a manifold, and you can go, wherever you want to go from there as far as equipment and other uses. So you pipe to domestic hot water, you can have radiators, you can have in-floor radiant, you can have panel radiators. So the manufacturers have really good, as I've found them to be, manuals and piping schematics from the manufacturer to help look at different configurations and help you define what the best piping would be and how to best set the system up. John Sigenthaler is kind of a well-known guru of hydronics, and he has created his own content, which is available online, and he's going to be at our Better Buildings by Design conference coming up here too to do a session. But he's also created a lot of content for manufacturers as well. And so there's a lot of good stuff out there on the market. There is good support I found from the manufacturers and distributor reps on helping to set up these systems as well too. So, there's some piping considerations to be learning in how to pipe these and set them up, and the wiring side of the equation as well. But again, just getting to the point that there's good support out there to help you if you're planning to put a system in and want to get the ins and outs of setup nailed down. See if there's a question here. See something coming in the chat. See a question from Ed here. Talk about using these systems for cooling during hot weather. How is condensation of humid air accounted for inside the low temp emitters? So that side of the equation, you're going to be needing to specify an emitter or a distribution type that can handle where you're going to be getting the potential for condensation. So, you know, panel radiators, I would not sure if you're going to have a panel radiator available that has condensate pan or drain in it that would be able to work for that function. But I'm just not aware, so I can't quote on that. But you know, more commonly, I think what you would find would be that you're going to be using some sort of hydrocoil and then ducted system, or one of the wall hung units in the building to do the cooling side of the equation. So, because otherwise you can't control that potential for condensation in a, you know, a radiant slab or a above floor or below floor radiant system as well too. Let's see if there's any other questions at the moment. So here's some pictures, some examples of installations that are in Vermont. This is an installation of a colleague of mine, Brian Justs, in Charlotte. So this is a retrofit application. Brian has a home with a radiant slab on grade, and for the first floor, and then the second floor had fin tube baseboard. And so a couple years ago, Brian replaced the gas boiler that was serving those zones and doing domestic hot water for the building as well too, I believe. And he retrofit the, he was able to lower the distribution water to the radiant slab without issue. And what he needed to do for the bedrooms on the second floor, where the fin tube baseboard was, that was removed and it was replaced with low temperature panel emitters in those spaces. So, you know, there was a bit of piping work to do. You know, he was able to get those old baseboards out and new piping run with PEX through the building where he needed to, without a lot of demo, you know, to get to the spaces that he needed it. And then replace the boiler with the Nordic air to water equipment. So this is the outdoor unit for the Nordic system. This is the indoor unit where that heat transfer occurs with your refrigerant to water. This is the buffer tank. The buffer tanks that are in place with this, manufacturers have their own specific buffer tanks. You can get other buffer tanks, but really one of the key elements of having that buffer tank is that there is an electric resistance element within the buffer tank to serve as a backup to the heat pump. So, you know, on days where you may have really cold outdoor temperatures and really high demand within the building, and if the heat pump is not able to keep up and maintain the set point in the tank, that resistance element in the tank will come on, boost the temperature of water for the distribution side, and maintain your distribution side of the equation until the heat pump can pick up more of that load once again. This is the new Spacepak inverter split system. So these this unit became available last year. It's a 5-ton capacity unit. The Spacepak is rated, and they have performance data down to 20 below. So, you know, the equipment is still generating heat energy at well below zero outdoor air temperatures. And again, you know, you're creating much lower BTUs at colder outdoor ambient conditions, but as long as the building envelope can is a good building envelope, and you're sizing your buffer tank also appropriately to what the space demands are, you know, you're really worried about just keeping that tank temperature in the buffer tank where it needs to be throughout the heating season and throughout those swings in indoor and outdoor temperature. So this is the indoor box of the Spacepak SIS equipment fed to the buffer tank here. This is retrofit that I did, or the new system I put in my house this past year. So this has just been this has been running since December at this point. This is the buffer tank that Spacepak sells with their equipment. So you can see these are actually 2 electric 20 kW coils in the buffer tank to augment the temperature if the heat pump can't keep up. You know, I live at 1,700 feet up in the hills in Shrewsbury, and we have a long cold winter. Had a lot of cold days, well below 0, and then 15 to 20 below 0 at times. And I did not see that the electric elements came on during the heating season this year. So just a closer look at these 2 items. So this is a 40-gallon buffer tank, again with the 20 kilowatt resistance heating element. Very straightforward and simple distribution side of the equation here. We had 2 primary zones for heating, and then the individual branch boxes that serve different parts of those 2 zones. So we have outdoor temperature reset to the heat pump itself. Each room, or not all rooms, but most rooms in the house have their individual thermostatic control. So we can adjust temperatures, you know, room by room with the branch box that we have. And the distribution side of the equation here was an above floor radiant panel system, or radiant tube system for all the floors throughout the building. Chose to go this route because to me, having that direct contact of the tubing and the emitters directly with the finished flooring into the room seemed to be the most efficient way and most uniform way to get space conditioning for what we were doing. So this is the Uponor Quick Track. So it's 1/2-inch plywood channeled to fit 5/16 tubing. And then on the underside of the plywood, you can't see it here, but there is aluminum sheet that runs under all of these pieces. So it's a pretty good monolithic emitter when you get the whole system fully installed. So that was the content that I had for you. I'm happy to stay on here for a bit and answer questions in the chat here. Can you use a typical or existing domestic hot water heat pump, so heat pump water heater, as a backup supply to air to water? I think that's what I'm seeing here from you, Harrison. And feel free to come on mic if you want to ask a question here as well too. All right, well, I'll address that as yeah, using an existing hot water heater or heat pump water heater, no, is kind of the answer. You know, the buffer tank is set up to be where you're storing your heat energy from the heat pump, and again, that there's a stratification that optimizes how that thermal battery or thermal storage is going to work. So the piping of the buffer tank is kind of specific to that purpose. So you're typically not going to be integrating, you know, your supply side of the equation through an existing tank, or, you know, something that's set up for water heating. You can, like I said, you can do domestic hot water with an air to water system, and that is typically, you know, you're not an individual heat pump water heater. You're using the heat pump to do your primary heating of the tank, but then you're backing it up with electric resistance. So, you know, depending on how much capacity you have with the heat pump for what the space heating needs are, you may have enough BTUs available to use for domestic hot water. Typically, you're going to need to be augmenting those BTUs with an electric resistance element in that domestic hot water tank, because oftentimes your distribution temperature side of the equation is not going to be aligned with what you need for domestic hot water use. So usually, you know, most of the components of getting an air to water system retrofit into an existing building are going to be integral to themselves, and then where that plugs in to the existing distribution side is to your piping and everything that goes out to your emitters in the building, the baseboard or radiant slab or whatever it is that's in place in the building for distribution. Leslie has a question: what would it cost to add on to an existing system? You know, that's going to be dependent on the existing distribution. So kind of to Kim's point earlier, it's not typically it's not a plug and play scenario to do something like this in a retrofit application. More often than not, you're going to have to modify the existing distribution in some way, shape, or form. You know, if you have radiant floor systems existing in a home, either, you know, one of the, you know, radiant tubing, PEX tubing systems to put above a framed floor system, or an in concrete sort of radiant slab, that can be more cost effective to replace or retrofit an air to water system into, because again, those are well suited to low temperatures for distribution. So in those scenarios, you're not needing to be replacing or augmenting what's in the building for distribution. But if you have, you know, existing fin tube baseboard or radiators in the building, you're going to typically need to be changing that in some way, shape, or form, or adding on to it. And that really, you know, how you get to that point comes from doing the right sort of load calculations necessary to size the system. So again, you need to know what each room needs for BTUs at design temperature and also throughout the heating season. And then from there, you can be doing calculations about what your, you know, distribution side needs to do. And that could be, that's the case if it's going to be hydronic, if it's going to be baseboard, fin and tube baseboard, or if it's going to be a furnace and forced air, and how many, you know, BTUs and CFM are coming from the ductwork as well too. Right. I don't know if people can come on mic, but feel free to do so if you have any other questions. We do have a survey, which I think Bryn dropped into the link or into the chat. So yeah, if you wouldn't mind taking a moment to just offer some feedback, that would be great. We do have our Better Buildings by Design conference coming up at the end of April. We moved it this year from February to the end of April. And we have some great content this year on air to water systems and ground source heat pumps. So really looking at the whole house heat pump system options, and both for retrofit and for new construction. So if you have interest in learning more, that'd be a great avenue to go to and get to sit in on some sessions and look at some projects that have been done in the state and meet with manufacturers, installers, and distributors as well.
Hey, Steve, you got one more question.
Sure. Does existing hydronic copper piping typically work to supply the emitters? Yeah, I don't, you know, if you're talking about replacing the emitter in a room, you know, taking baseboard out and putting in a panel radiator, I'm sure you're gonna have to do some calculations as to the loss of, you know, within that tubing from the manifold to the emitter, but I don't know of any limitations to using existing you know, supply lines through the building, as long as it's the right diameter pipe, of course, too. I mean, it's got to match the flow of what the emitter would require. So yeah, and the retrofit side of things, it's all going to be very circumstantial to the what's existing to define those answers more effectively. All right, well, we are at 9, so I want to thank you all for joining us this morning, and my contact information is here. So if you have further questions, you want to talk about a project you're working on, you know, in particular in more detail, please feel free to reach out to me. and maybe we'll see some of you at the Better Buildings Conference here at the end of April. So thank you. Have a great day. Have a good weekend. Take care.